A power series is like an infinite polynomial. Let me show you what I mean. We all know what a polynomial is. Let's say we want a polynomial of degree n. So we could write it as the sum. I goes from 0 to n, ai, x to the power of I. That's a bit abstract. If you put it in regular notation without sigma, it's a naught plus a1x, x to the 1, plus a2x squared, plus and so on, up to an x to the n. And we write it in increasing powers of x, more convenient. When it's a polynomial of degree 2, we might just write ax squared plus bx plus c, but we run out of letters, so we write it from decreasing to increasing powers. This might be written as a naught plus a1x plus a2x squared. Then we generalize it to degree n, and now I want to make one more generalization to change this n to infinity. So a power series, very much like this, it's just that we take from 0 to infinity, but I'm going to use the letter n instead of I. So I'll say n goes from 0 to infinity, an x to the n, and if I write it out in expanded form, it looks like this: a naught plus a1x plus a2x squared, only it doesn't stop, it keeps on going forever. And let me give an example. I'll give a few examples. In fact, let's start with example 1. I'll take the sum from 0 to infinity of 2 to the n, x to the n. And if I write this out, this is like 1 plus 2x plus 2 squared, which is 4x squared. I'll write another term, 2 cubed is 8, x cubed plus and so on and so on. And sometimes we could just briefly describe this by just saying what an is in this formula. Here we would say an is 2 to the power of n, and that would describe this series based on this. Let's give another example, and this one will be example 2, of course. This time I'll take the sum of 1 over n, x to the n, only I can't take it from 0 to infinity, because when n is 0, we would be dividing by 0, so we'll take it just from 1 to infinity. And that's another thing. The power series doesn't necessarily have to start at 0. And this would equal, if n is 1, we get x to the 1 over 1, which I would write just as x, plus x squared over 2, plus x cubed over 3, plus and so on. And here I could describe this by saying an equals 1 over n, but I'd also have to make a note that we start from 1. Let's take yet another example. This time I'll take the sum, also from 0 to infinity, of 2 to the n over n factorial x to the n. And this would equal 2 to the 0 over 0 factorial, x to the 0, I don't write that, 2 to the 1 over 1 factorial x, 2 squared over 2 factorial x squared, I'll write one more, 2 cubed over 3 factorial x cubed, and so on. And yet another example, and this time it's given in a slightly different form. Sometimes you have to modify it a bit. I have minus 2x over n to the power of n, and then I might just have to break it open a bit to get minus 2 over n to the power of n, and then x to the power of n, just using the rules of exponents, taking the x to the n outside the brackets. Okay, that's enough examples. Now the next topic I want to talk about is convergence. Okay, so specifically I'm going to talk about something called region of convergence, and I'm going to illustrate with an example. Let me keep example 2, and I'll move it up here. Now, a power series is like a polynomial, but infinite, but it's like a polynomial also in the sense that we can substitute different values of x and get a result. Now, what happens if here, for example, if I substitute x equals 1? If I put x equals 1, then I get the sum n equals 1 to infinity. 1 to the n is just 1, so I get the sum of 1 over n, and if I write it out, it's 1 over 1 plus 1/2 plus 1/3 plus 1/4 plus and so on. And this is a specific series, not depending on x, and as a number series, which we've studied, there could be two possibilities, or actually three. I'd like to remind you that a number series can have possibilities. It could diverge, or it could converge. And actually the converge we can split into two cases: converge conditionally, I'll just write conditionally, or it could converge absolutely. So absolutely. And the question is, what happens in this particular case? If x is 1, this is the harmonic series, and we know it diverges. So I'll write diverges. Let's take another example. Suppose I put x equals -1. Then I get the sum from 1 to infinity. If I put x as -1, I get -1 to the n over n. And if we expand this, we get, when n is 1, we get -1 plus 1/2 minus 1/3 plus 1/4, and so on. And it turns out that this converges. Won't get into too much detail, but if you remember series, this is an alternating Leibniz series. It's plus minus, and so on. And if I ignore the sign, it's a series that decreases and goes down to 0. 1, 1/2, 1/3, 1/4, keeps getting smaller and smaller and tends to 0. Let's take a third example. X equals 0. When x is 0, we get the sum from 1 to infinity. 0 to the n is just 0, so each term is 0, and this definitely converges, and I can even tell you what the sum is. The sum is 0, but the point is that it converges. And not only that, but in general, the sum for any power series a n x to the n goes from something, could be 0, could be something else, to infinity, always converges for x equals 0. So that's one thing we can count on, is that. Now, what I want to discuss here is that for some values of x we can substitute it will converge, for some it will diverge, and if it converges for some values it will converge absolutely, and for some values conditionally. And we want to see, other than haphazardly trying each value, if I can some way tell from the series for which values of x it's going to converge and for which values of x it's going to diverge, and so on. Is there a general rule that we can find out? Just like to get one more example in before I discuss in general. Let's just try x equals 2, and then we get the sum from 1 to infinity of 2 to the n over n, and I claim that this diverges. And one of the ways of proving divergence, the easiest, if it's possible, is to show that the general term does not tend to 0. In fact, the limit as n goes to infinity of 2 to the n over n is infinity. There's many ways of showing this. One way would be to use the function 2 to the x over x, and then use L'Hopital's rule. I don't want to get into this too much. Anyway, this does not, it goes to infinity, it does not go to 0. So if the general term doesn't tend to 0, then the series diverges. Okay, now we've got some values, and let me now just tell you, I'll give you the answer for which values of x this series converges without explanation, and then we'll discuss it in more detail. I'll tell you that it converges when x is between 1 and -1, but it includes the -1 and does not include the 1. Never mind how we got to this, that will be later. I'm just giving you the answer. It always turns out that it's in an interval, in this case from -1 to 1, and sometimes including the endpoint, sometimes not. But the set of values for which it converges is called the range of convergence. That's one name for it. And more commonly, now that we know that I'm telling you that it's going to always be continuous as an interval, it can't be like, for 3 it will converge, for 4 it will diverge, then from 5 to 6 suddenly converge again. It's always a contiguous interval, so it's sometimes called the, in fact more commonly called the interval of convergence. And I've even seen region of convergence, so range, interval, region of convergence. Now let me give the general rule, a theorem, and then we'll also see how, in this example, how I got to this result which I quoted without showing you why. The set of values for which the series converges has many names. It's called the region of convergence. It's just, as I say, the set of values for which the set of values of x for which the series converges. In this case, we can see it's an interval. In fact, it always turns out to be some kind of interval, so it's also called the interval of convergence, and sometimes the range of convergence. So all these three are possible: region of convergence, interval, range. And now I'm going to give a theorem about what we can expect